Section: Introduction. Language models, LMs, are becoming increasingly popular as tools for fact-checking and information sourcing. However, they are not without their flaws. They often generate incorrect information, contradict themselves, and struggle to incorporate new information. Despite these shortcomings, LMs are quite adept at identifying logical and probabilistic relationships between statements and generating text based on new input. For instance, an LM might not be able to answer the question, "How old was Charlie Chaplin when he died?" but it could provide a correct answer when given the information. Charlie Chaplin lived between 1889 and 1977, and recognize that this contradicts the claim, Charlie Chaplin lived in the 21st century. The challenge lies in harnessing the LM's ability to reason about factual relationships to improve the text it generates. Even if a piece of information is included in an LM's training data, updating the LM's parameters to increase the likelihood of sentences containing this information doesn't necessarily increase the likelihood of sentences describing its logical consequences. In other words, fine-tuning a definition doesn't guarantee that an LM will assign a higher probability to uses of the newly defined word. To address this, we propose a new LM fine-tuning procedure called Deductive Closure Training, DCT. This method uses reasoning at the time of inference as a source of supervision during training. In simple terms, DCT uses an LM to identify additional text that is implied by or contradicts the seed text, which could be externally provided or generated by the LM, reason globally about which parts of the seed and generated text are most likely to be correct given this context, and finally fine-tune on the inferred correct text. DCT can be used in several ways depending on the source of the seed documents. If the documents are from a trusted factual source, DCT can be used to perform supervised adaptation for factuality. If the documents contain new information to be inserted into an LM, DCT provides a tool for model updating. If the seed documents are generated by the model itself, DCT enables fully unsupervised fine-tuning of models for improved accuracy. We tested DCT across 3 domains: fact verification, question answering with new information, and a synthetic test of edit propagation. In these tasks, unsupervised application of DCT improved accuracy by up to 12%, while supervised application improved accuracy by up to 26%. These results suggest that problems such as model coherence and editing may not require specialized editing or training techniques. DCT builds on several recently developed techniques for improving model accuracy. Some research has focused on bootstrapping language model performance at inference time, while others have focused on supervised learning for factuality. Past work has also studied leveraging LMs themselves for performance improvements. DCT aligns with these approaches in its aim to improve model training, but it differs by requiring minimal or no external supervision. Section Summary. Today's language models, LMs, have limitations in fact verification and generating accurate information. However, they excel at identifying logical and probabilistic relationships between statements and can generate text based on new information. To leverage this ability, the authors propose a new LM fine-tuning procedure called Deductive Closure Training, DCT, which uses inference time reasoning as training time supervision. DCT can be used for supervised adaptation, model updating, or fully unsupervised fine-tuning, and it improves accuracy by up to 26% in fact verification, question answering, and edit propagation tasks. DCT builds on previous work in bootstrapping accuracy during inference, supervised learning for factuality, and self-training techniques. Section: Method. Let's break down the method used in this research. We start with a language model, which we'll call P_LM. This model assigns probabilities to different strings of text. Our aim is to fine-tune this model so that it's both coherent and complete. By coherent, we mean that if the model assigns high probabilities to 2 statements, those statements should be compatible. By complete, we mean that if the model assigns a high probability to a statement, and that statement implies another, the model should also assign a high probability to the implied statement. These two properties together mean that the model is logically consistent, which is a necessary condition for it to be truthful. The process of training the model to be logically consistent starts with a set of seed documents. These could be facts from a trusted source, new information provided by a user, or even text generated by the model itself. The model is then used to generate additional text that is either implied by each seed document or contradicts it. For example, if the seed text is, "Country music originated in the United Kingdom," the model might generate statements like, "The UK is famous for country music," or question-answer pairs like, "Where did country music originate?" England. Once these additional documents have been generated, the model is used to identify which of them are most likely to be true. The model is then fine-tuned based on these most likely true documents. The first step in this process is to generate a set of related documents for each seed document. This is done by constructing a set of textual prompts that instruct the model to generate other documents that are either implied by the input or contradict it. These prompts are then used to generate a collection of related documents for each seed document. The seed document is included in this collection, which is important for detecting and correcting errors in the seed document itself. This generation step may be followed by a double-checking step, in which the model is used to verify whether the seed document implies or contradicts each related document, and any related documents that the model does not confirm with high probability are discarded. The next step is to evaluate the consistency of the collection of documents. These documents may contradict each other, and the aim is to identify the subset that is most likely to be collectively true. This is done by using the model to classify the logical relations between the documents, and to assign a prior probability to each document. For example, if it is true that Emperor Meiji was the first emperor of modern Japan, it cannot also be true that Emperor Meiji was the last Japanese emperor. If the first statement is very likely to be true, then the second statement is likely to be false. Each document is associated with a truth value, and the model's probability of this assignment is computed. The model is then used to estimate the probability that each document is true. This is done by conditioning the model on a small set of document label pairs, where the labels are either true or false. A value assignment is defined to be consistent if all implications and contradictions are respected. The most probable consistent assignment is then selected. This procedure is depicted in the figure, with the highest scoring truth value assignment shown in the blue highlighted box. Section Summary. The goal of our method is to optimize a language model, LM, so that it is coherent and complete, meaning it assigns high probability to compatible statements and their implications. We achieve this by training the LM on a set of seed documents, generating related documents using the LM, and then using the LM to reason about the consistency of these documents and select the most probable ones. Section. Language Model Fine-Tuning. We'll now discuss the process of fine-tuning our language model, which we'll refer to as PLM. We only fine-tune PLM on the documents we've identified as true. We don't train PLM until it's perfect, but rather for a set number of iterations. The way we use our fine-tuning process depends on how we get our initial documents, which we call seed documents. Here are a few ways we can use it. 1. Unsupervised fine-tuning for coherence. In this case, we get our initial seed set from PLM itself. For example, we might ask it to generate a set documents on a specific topic. 2. Semi-supervised alignment with a trusted source. Here, the seed set comes from an external source of supervised data. If we know this data is reliable, we set each seed document's truth value to 1 during the evaluation step. We can combine this with the unsupervised procedure. 3. Model updating, editing, and continual learning. In this case, we treat descriptions of desired edits as seed documents, set their truth values to 1, and fine-tune on these documents and their implications only. In the last two cases, where we've set the truth value of seed documents to 1, the evaluation step is much simpler. It just discards all generated documents that aren't logically consistent with the seed. In the case of unsupervised learning, this evaluation step can cause language models to relabel sampled seed documents as well as conditionally generated ones. The procedure we've described is a basic implementation of a family of similar approaches. There are many more sophisticated procedures possible, such as probabilistic DCT, contrastive DCT, and multi-hop DCT. At first, it might seem surprising that this procedure can improve the accuracy of a language model using only text generated by the model itself. But under certain assumptions, DCT is guaranteed to improve accuracy on certain inputs. We'll focus this analysis on generating and evaluating pairs of questions and answers, but it could be extended to other tasks as well. Suppose that questions generated by the language model with high probability are likely to be correct. Also, suppose that prompting a language model with a related, correct question-answer pair increases the probability of a correct answer. If these two conditions hold, DCT improves model performance. For simplicity, let's consider a minimal version of unsupervised DCT. In this version, a single implication is generated from each seed statement, the check-in EQ. Consistency is not performed, and the language model is trained to convergence on data generated from an arbitrarily large number of seeds. Let's say we have a specific question of interest, Q. Let PLM, A*Q, denote the probability that PLM assigns the correct answer to Q before applying DCT, and PDCT, A*Q, be the probability that the language model assigns after DCT. Let Q0, A0, denote a question-answer pair generated as a seed document, and A0*, specifically the correct answer to Q0. Now, suppose for some question Q that 1. The probability that the generated answer to any seed question Q0 contains a correct answer is at least P. 2. In expectation, conditioning on a correct Q0, A0 pair increases the probability of generating a correct answer by at least 1 P. If these two conditions are met, unsupervised DCT increases the probability that PLM answers Q correctly. We provide a proof of this in the appendix. Section Summary. Language Model Fine-Tuning, LMFT, is performed on inferred true documents, optimizing the parameterized LM probability distribution. Seed data can be obtained through unsupervised fine-tuning, alignment with a trusted source, or model updating. DCT can be generalized to probabilistic DCT, contrastive DCT, and multi-hop DCT. The formal analysis of DCT shows that if high-probability questions are likely to be correct and prompting with correct question-answer pairs increases the probability of a correct answer, then DCT improves model performance. Section. Experiments. We put our deductive closure training, DCT, to the test on a variety of tasks, including fact-checking, answering questions with new information, and editing models. We used the Llama 2-7B model for all our experiments. First, we wanted to see if our method, known as AC, could improve the model's ability to determine if a statement is true or false. We used a dataset called Creek, which contains claims about different entities. We tested 4 different learning settings: unsupervised, supervised, semi-supervised, and transductive. Each setting used a different method for selecting initial documents. We then fine-tuned our model using DCT until the training loss stabilized, which usually took around 30 epochs. We evaluated our models based on how accurately they could label claims as true or false. We compared our results to the best existing models for each data condition. For unsupervised DCT, we compared our model to a simple few-shot prompt. For supervised DCT, we compared our model to one that was fine-tuned on true statements. For transductive DCT, we compared our model to a graph inference model, which generates implications and contradictions for each test example, then directly outputs the inferred truth value for the example. In the unsupervised DCT experiment, we asked the model to generate 10 diverse claims 10 times, and then filtered out any duplicates. Our method significantly outperformed the few-shot prompting baseline, and may even outperform a version of DCT that only fine-tunes on high-priority seed statements. We also evaluated our model's logical coherence and factual accuracy using a contrast set in Creek, which contains 250 pairs of similar examples with opposite truth values. Our DCT method not only improved accuracy but also reduced the number of incoherent predictions. In the supervised and semi-supervised DCT experiments, we used a small set of externally provided claims and their corresponding truth labels to initialize DCT seed nodes. For semi-supervised learning, we combined data generated from the unsupervised and supervised settings for fine-tuning. All versions of DCT improved over a simple fine-tuning baseline. In the transductive DCT experiment, we had access to unlabeled claims from the evaluation set while updating the model. For each claim in the validation set, we generated seed text by prompting the model to generate a set of related claims. DCT outperformed the inference time reasoning baseline as well as the related text-only ablation in these experiments. Language models often generate incorrect information and quickly become outdated after initial training. Therefore, there's a growing interest in specialized continual learning procedures for updating models with new information without having to retrain them completely. We used the counterfactual subset from the MQUAKE dataset for our experiments, which evaluates models on their ability to answer questions about new information not provided in their training sets. We used the text of the new information as seed documents and prompted the models to combine this information with other related knowledge, producing what we call correlative implications. Finally, we converted each generated statement into a question-answer pair using the model, then fine-tuned it on these pairs. Section summary. The experiments conducted evaluate deductive closure training, DCT, on various benchmark tasks, including fact verification, question answering with new information, and model editing. The experiments use different learning settings, such as unsupervised, supervised, semi-supervised, and transductive, and compare the results to state-of-the-art baselines. DCT shows improvements in terms of accuracy, logical coherence, and reducing incoherent predictions, making it a promising approach for updating language models with new information. Section: Evaluation and Baselines. We're comparing our method, Dynamic Contextual Tuning, DCT, with standard fine-tuning and two other advanced methods for updating models. One of these methods is a self-training approach that adjusts language models to behave the same way with or without prompts containing new information. The other method, called Mellow, stores new text in an external memory. We tested DCT and these other methods by providing them with different amounts of new information, ranging from 10 to 1,000 pieces, and then assessed their accuracy in answering questions. Our results show that DCT performs significantly better than standard fine-tuning on continuations, and Mellow, which was previously the best method on the MQUAKE benchmark. We found that using correlative implications consistently improves performance over simple implications. Combining both types of implications further enhances performance. Our detailed analysis reveals that using correlative implications in statements provides about 50% more new information than using standard implications. In addition to real-world question-answering tasks like MQUAKE, we're also interested in testing language models' ability to understand simple logical implications of new facts. For example, if a model is trained on sentences like A is B, it should be able to assign a high probability to sentences like B is A. We tested DCT on this using the reversal curse benchmark, which includes two evaluations, one with celebrity parent-child pairs and another with entity description pairs. For these experiments, we compared DCT to the standard fine-tuning method and the fine-tuning on continuations approach. We used training examples as seed statements and generated implications using the same prompt as in the Creek experiments. Our goal was to see if a general-purpose prompt could improve performance on a specific type of generalization. We reported exact match accuracy after removing punctuation and converting to lowercase. In this dataset, language models are evaluated on a mix of questions and close completion tasks featuring both training statements and their reversed forms. Our results show that, on average, DCT improves accuracy on reversed statements without significantly hurting performance on original questions. However, DCT with this general-purpose prompt doesn't completely solve this dataset. We're leaving it for future work to explore whether more extensive sampling or other procedures could further improve these results. To better understand how DCT improves language model performance, we manually annotated about 350 generations from various experiments. We wanted to see if double-checking improves the precision of generated implications and contradictions, if DCT incorporates model internal knowledge when making new conclusions, and if generated text includes non-trivial new inferences. Our evaluation shows that the double-checking process following DCT improves precision. In a supervised setting, we annotated 100 implications and contradictions generated using DCT. We found that 74 of these are valid. The double-checking procedure removes about 2/3 of generations, resulting in 33. Among these, 27 are valid, raising the ratio of correct statements predicted by the model from 76% to 82%. The MQUAKE subset used in our experiments includes difficult multi-hop questions. Therefore, generations that incorporate existing information about the entities mentioned in the edit are particularly useful. We compared the set of implications generated using DCT and found that only 30% and 36% of generations involve strict logical implications. However, 78% and 69% were judged to be plausible given the edit. Furthermore, 24% and 33% of the generations incorporate new information supplied by the language model. Lastly, we found that the implications made by the model on the reversal curse dataset vary from trivial to rarer ones, adding world knowledge to the implication. While generating implications, DCT often generates test set-like reversed implications on its own. These findings suggest a strong bias towards generating text that actually starts with the person as opposed to description. In general, most generated extensions are fluent, different from the source, and sometimes contain new information.